When a transformer is energized and the breaker feeding it trips, several potential causes should be considered. Firstly, inrush current. When a transformer is initially energized, it draws a high initial current called inrush current, which can significantly exceed the normal steady-state current. This surge can cause the breaker to trip, especially if the breaker settings are set too low or are very sensitive. Secondly, ground fault. A ground fault, whether on the primary or secondary side of the transformer, is a common cause of breaker tripping. The tripping action could be due to the overcurrent resulting from the fault or the activation of a ground fault detection feature within the breaker itself. Thirdly, loose connections. Loose connections on either the primary or secondary side of the transformer can introduce resistance into the circuit. This resistance can generate heat and lead to breaker tripping over time, as the increased temperature affects the conductors and the connection points. Fourthly, overload. Even when the transformer is disconnected from its secondary load, it remains connected to the primary power source. If this primary power source delivers voltage or current that exceeds the transformer's rated capacity, it can cause the breaker to trip as a protective measure. To effectively troubleshoot this issue, follow these steps. 1. Check for ground faults. Employ a megometer, also known as a megger, to test for ground faults on both the primary and secondary sides of the transformer. This tool applies a high voltage direct current to measure insulation resistance, helping identify any leakage to ground. 2. Check connections. Conduct a thorough visual inspection of all connections on both the primary and secondary sides of the transformer. Ensure that all connections are tight and secure to eliminate any potential points of resistance or arcing. 3. Measure inrush current. If feasible, connect an ammeter to the primary side of the transformer to directly measure the inrush current upon energization. Compare the measured inrush current value against the breaker settings to determine if the inrush current exceeds the breaker's tripping threshold. 4. Monitor voltage and current. Connect both a voltmeter and an ammeter to the primary side of the transformer. Monitor the voltage and current being supplied by the primary power source to ensure that these values remain within the transformer's specified rated limit. 5. Consult the manufacturer. Reach out to the transformer manufacturer for specific guidance on troubleshooting the issue, as well as for recommended breaker settings that are suitable for the transformer's characteristics and application. Several additional considerations may also prove useful. The ground fault circuit interrupter feature, also known as GFCI, in the breaker might be overly sensitive and contributing to the tripping issue. As a diagnostic step, consider temporarily disabling the GFCI feature to determine whether the tripping problem persists. It's critical that a comprehensive coordination study be conducted. Once finalized, the coordination study will offer detailed guidance on selecting appropriate breaker settings. Adhering to the recommendations outlined in the study will ensure proper coordination between the breaker and the transformer, providing optimal protection for the electrical system. It is also good to note that you will need some tools. You may need a multimeter to measure voltage, current, and resistance. An insulation resistance tester, also known as a megometer or megger, to test the insulation of the transformer windings and cables. An ammeter, clamp-on or in-line, to measure the current flowing through the circuit. Safety equipment like gloves, safety glasses, and appropriate personal protective equipment. Before working on any electrical equipment that energize the circuit, and verify that it is de-energized using a multimeter. Follow all safety precautions and wear appropriate personal protective equipment. If you are not comfortable working on electrical equipment, consult a qualified electrician. When a transformer is first energized, it experiences a phenomenon known as inrush current. This is a very high instantaneous current that flows into the transformer's primary winding as the magnetic core is being magnetized. The magnitude of the inrush current can be several times higher than the transformer's rated full load current. The inrush current is caused by the sudden application of voltage to the transformer winding. At the instant of energization, the magnetic core is unmagnetized, so it offers very little impedance to the flow of current. As a result, a large current flows into the winding, limited only by the winding's resistance and the source impedance. The duration of the inrush current is typically very short, lasting only a few cycles of the alternating current waveform. However, its high magnitude can be sufficient to trip circuit breakers or blow fuses that are designed to protect the transformer from overloads. Several factors can affect the magnitude and duration of the inrush current. These factors include the size and design of the transformer, the impedance of the source supplying power to the transformer, the point on the voltage waveform at which the transformer is energized, and the residual flux in the transformer's core. Transformers with larger kV amps ratings tend to have higher inrush currents. Transformers designed with lower impedance also tend to have higher inrush currents. Energizing a transformer at the voltage waveform's peak can result in a higher inrush current than energizing it at the voltage waveform zero crossing. Residual flux, which is the magnetic flux remaining in the core from a previous energization, can either increase or decrease the inrush current depending on its polarity. To mitigate the effects of inrush current, several techniques can be employed. Firstly, using slow blow fuses. Slow blow fuses are designed to withstand temporary overcurrents such as inrush current without tripping. Secondly, using circuit breakers with instantaneous trip settings. Circuit breakers with adjustable instantaneous trip settings can be set to allow for the passage of inrush current without tripping. Thirdly, using pre-insertion resistors. Pre-insertion resistors can be temporarily inserted in series with the transformer winding during energization to limit the inrush current. Once the inrush current has subsided, the resistors can be bypassed. Fourthly, using soft starters. Soft starters are electronic devices that gradually increase the voltage applied to the transformer winding during energization, thereby reducing the inrush current. Understanding inrush current is crucial for the proper protection and operation of transformers. By taking appropriate measures to mitigate the effects of inrush current, you can prevent nuisance tripping of circuit breakers and ensure the reliable performance of your electrical system. The secondary conductors are disconnected, so that rules out any secondary ground faults. However, we can investigate for primary ground faults. Ground faults are unintended electrical connections between a live conductor and ground. They can occur due to damaged insulation, loose connections, or equipment failure. Ground faults are dangerous because they can cause electric shock, fires, and equipment damage. Ground fault protection is designed to detect and interrupt ground faults quickly, minimizing the risk of these hazards. There are two main types of ground fault protection. Firstly, ground fault circuit interrupters or GFCIs. Ground fault circuit interrupters are devices that detect ground faults by monitoring the current balance between the hot and neutral conductors in a circuit. If there is a difference of more than a few milliamps, the GFCI will trip, interrupting the circuit and preventing electric shock. Secondly, ground fault relays. Ground fault relays are used in larger electrical systems to protect equipment from ground faults. They typically consist of a current transformer that monitors the current flowing through the ground conductor and a relay that trips a circuit breaker if a ground fault is detected. Ground fault protection is required by electrical codes in many applications, including residential, commercial, and industrial settings. The specific requirements vary depending on the type of occupancy and the electrical system voltage. Ground fault protection is an essential safety feature that can prevent serious injuries and property damage. It is important to ensure that ground fault protection is properly installed and maintained to ensure its effectiveness. To check for ground faults, you can use a multimeter or a ground fault tester. A multimeter can be used to measure the resistance between the hot and neutral conductors and ground. A low resistance reading indicates a ground fault. A ground fault tester is a specialized device that is designed to detect ground faults. It works by injecting a small current into the ground conductor and measuring the voltage drop. A voltage drop indicates a ground fault. If you suspect a ground fault, it is important to energize the circuit and call a qualified electrician to investigate. Do not attempt to repair a ground fault yourself unless you are a qualified electrician. Loose connections can cause a variety of problems in electrical systems. They can create resistance, which can generate heat and cause the breaker to trip. They can also cause voltage drops, which can affect the performance of equipment. In addition, loose connections can create a fire hazard. There are several reasons why connections can become loose. Firstly, vibration. Vibration can cause connections to loosen over time. Secondly, corrosion. Corrosion can weaken connections and cause them to become loose. Thirdly, thermal expansion and contraction. Thermal expansion and contraction can cause connections to loosen and tighten over time. There are several ways to prevent loose connections. Firstly, use properly sized connectors. Properly sized connectors will provide a secure connection that will not loosen over time. Secondly, tighten connections properly. Connections should be tightened to the manufacturer's specifications. Thirdly, use lock washers. Lock washers will help to prevent connections from loosening over time. Fourthly, inspect connections regularly. Connections should be inspected regularly for signs of looseness or corrosion. If you find a loose connection, tighten it immediately. If you find a corroded connection, clean it or replace it. The primary power source may be supplying more voltage or current than the transformer can handle. Transformers are designed to operate within specific voltage and current ranges. Exceeding these limits can lead to various problems, including overheating, insulation breakdown, and ultimately transformer failure. Voltage overload occurs when the voltage applied to the primary winding of the transformer exceeds its rated voltage. This can happen due to voltage surges, line voltage fluctuations, or incorrect transformer tap settings. When a transformer is subjected to overvoltage, the magnetic core can become saturated, leading to excessive current draw, increased heat generation, and potential damage to the insulation. Current overload occurs when the current flowing through the transformer windings exceeds its rated current. This can be caused by excessive load on the secondary side of the transformer, short circuits, or ground faults. When a transformer is overloaded, the windings can overheat, leading to insulation breakdown and potential transformer failure. To prevent voltage and current overloads, it is essential to ensure that the transformer is properly sized for the application and that the voltage and current supplied to the transformer are within its rated limits. Proper overcurrent protection devices, such as circuit breakers and fuses, should be installed to protect the transformer from overloads and short circuits. Regular monitoring of voltage and current levels can help identify potential overload conditions before they lead to transformer damage. If you suspect that the primary power source is supplying more voltage or current than the transformer can handle, it is important to take the following steps. Firstly, verify the transformer's voltage and current ratings. Check the transformer's nameplate to determine its rated voltage and current limits. Secondly, measure the voltage and current supplied to the transformer. Use a voltmeter and ammeter to measure the voltage and current being supplied to the primary winding of the transformer. Thirdly, compare the measured values to the transformer's ratings. If the measured voltage or current exceeds the transformer's rated limits, take steps to reduce the voltage or current. Fourthly, check for any signs of transformer distress. Inspect the transformer for any signs of overheating, such as discoloration, bubbling, or unusual odors. If you observe any of these signs, it is important to de-energize the transformer and consult a qualified electrician. A megometer, also known as a megger, is an instrument used to measure the insulation resistance of electrical equipment. It applies a high direct current voltage to the insulation and measures the resulting current flow. The insulation resistance is then calculated using Ohm's law. Megometers are used to test the insulation of a wide variety of electrical equipment, including cables, transformers, motors, and generators. They are also used to test the insulation of electrical wiring in buildings. The insulation resistance of electrical equipment is an important indicator of its condition. A low insulation resistance indicates that the insulation is damaged and may need to be repaired or replaced. Megometers are available in a variety of voltage ranges from 500 volts to 15,000 volts. The appropriate voltage range for a particular application depends on the voltage rating of the equipment being tested. When using a megometer, it is important to follow the manufacturer's instructions carefully. Before testing, the equipment should be de-energized and isolated from all other circuits. The test lead should be connected to the equipment according to the manufacturer's instructions. The test voltage should be applied for a specified period of time, typically 1 minute. The insulation resistance reading should be recorded and compared to the manufacturer's specifications. If the insulation resistance reading is below the manufacturer's specifications, the insulation is damaged and may need to be repaired or replaced. Regularly testing the insulation resistance of electrical equipment can help to prevent electrical failures and ensure the safety of personnel. When visually inspecting connections on the primary and secondary sides of the transformer, check for loose wires. Loose wires can cause a variety of problems, including arcing, overheating, and power outages. Arcing can occur when a loose wire comes into contact with another conductive surface. The arcing can generate heat, which can melt the insulation on the wires and start a fire. Overheating can occur when a loose wire creates resistance in the circuit. The resistance causes the wire to heat up, which can damage the wire and surrounding components. Power outages can occur when a loose wire completely disconnects from the circuit. This can cause the power to go out to the entire circuit or to a portion of the circuit. To check for loose wires, visually inspect all of the connections in the primary and secondary sides of the transformer. Look for wires that are not securely fastened to the terminals. Also, look for wires that are frayed or damaged. If you find any loose wires, tighten them immediately. If you find any frayed or damaged wires, replace them. It is important to use the proper tools when tightening or replacing wires. Use a properly sized screwdriver or wrench to tighten the connections. Do not over-tighten the connections, as this can damage the wires or terminals. When replacing wires, use wires of the same gauge and type as the original wires. Also, be sure to properly insulate the connections after you have tightened them. In addition to checking for loose wires, it is also important to check for corrosion. Corrosion can occur when moisture or other contaminants come into contact with the metal surfaces of the connections. Corrosion can cause the connections to become loose or to fail completely. To check for corrosion, visually inspect all of the connections on the primary and secondary sides of the transformer. Look for any signs of rust or other corrosion. If you find any corrosion, clean the connections with a wire brush or other abrasive material. Then, apply a corrosion inhibitor to the connections to prevent future corrosion. If the connections are severely corroded, you may need to replace them. It is important to use the proper tools and materials when cleaning or replacing corroded connections. Use a wire brush or other abrasive material to clean the connections. Then apply a corrosion inhibitor to the connections to prevent future corrosion. When replacing connections, use connections of the same type and size as the original connections. Also, be sure to properly insulate the connections after you have cleaned or replaced them. If possible, connect an ammeter to the primary side of the transformer to measure the inrush current. An ammeter is an instrument used to measure the current flowing through a circuit. There are two main types of ammeters. Firstly, clamp-on ammeters. Clamp-on ammeters are non-contact devices that measure the current flowing through a wire by clamping around it. They are convenient to use because they do not require the circuit to be broken. Secondly, inline ammeters. Inline ammeters are connected directly into the circuit to measure the current flowing through it. They are more accurate than clamp-on ammeters, but they require the circuit to be broken to be installed. To measure the inrush current of a transformer, it is best to use an inline ammeter. This will provide the most accurate reading. However, if an inline ammeter is not available, a clamp-on ammeter can be used. When using a clamp-on ammeter, it is important to clamp it around only one wire at a time. Clamping it around multiple wires will result in an inaccurate reading. To measure the inrush current, connect the ammeter to the primary side of the transformer. Then energize the transformer. The ammeter will display the inrush current. The inrush current is typically very high, several times the normal operating current of the transformer. The inrush current will only last for a short period of time, typically a few cycles of the alternating current waveform. After the inrush current has subsided, the ammeter will display the normal operating current of the transformer. Compare the measured inrush current to the breaker settings. The breaker settings are the current and time values at which the breaker will trip. If the measured inrush current exceeds the breaker settings, the breaker will trip. If the breaker trips repeatedly when the transformer is energized, it may be necessary to increase the breaker settings. However, it is important to consult with a qualified electrician before increasing the breaker settings. Increasing the breaker settings can reduce the protection that the breaker provides to the transformer. Connect a voltmeter and ammeter to the primary side of the transformer to monitor the voltage and current supplied by the primary power source. A voltmeter is an instrument used to measure the voltage between 2 points in a circuit. An ammeter is an instrument used to measure the current flowing through a circuit. By monitoring the voltage and current supplied to the transformer, you can ensure that they are within the rated values of the transformer. If the voltage or current exceeds the rated values, the transformer can be damaged. To connect a voltmeter and ammeter to the primary side of the transformer, you will need to use a multimeter. A multimeter is a versatile instrument that can measure voltage, current, and resistance. To measure voltage, connect the voltmeter leads of the multimeter to the two terminals of the primary winding of the transformer. Select the appropriate voltage range on the multimeter. Energize the transformer and read the voltage on the multimeter display. To measure current, connect the ammeter leads of the multimeter in series with the primary winding of the transformer. Select the appropriate current range on the multimeter. Energize the transformer and read the current on the multimeter display. Ensure that the voltage and current are within the rated values of the transformer. The rated values of the transformer are typically printed on the transformer's nameplate. If the voltage or current exceeds the rated values, take steps to reduce the voltage or current. Steps you can take includes adjusting the voltage tap on the transformer, reducing the load on the transformer, and increasing the size of the conductor supplying power to the transformer. Contact the transformer manufacturer for guidance on troubleshooting and recommended breaker settings. The transformer manufacturer is the best source of information for troubleshooting problems with your transformer. They can provide you with specific guidance on how to troubleshoot your transformer, and they can also provide you with recommended breaker settings. To contact the transformer manufacturer, you can find their contact information on the transformer's nameplate or on their website. When you contact the transformer manufacturer, be sure to have the following information available. Firstly, the transformer's model number. Secondly, the transformer serial number. Thirdly, a description of the problem you are experiencing. The transformer manufacturer will use this information to help you troubleshoot your transformer and to provide you with recommended breaker settings. The GFCI feature in the breaker may be contributing to the tripping. A ground fault circuit interrupter, or GFCI, is a device that protects people from electric shock by monitoring the current balance between the hot and neutral conductors in a circuit. If there is a difference of more than a few milliamps, the GFCI will trip, interrupting the circuit and preventing electric shock. GFCIs are required by electrical codes in many applications, including bathrooms, kitchens, and outdoor outlets. However, GFCIs can sometimes nuisance trip, especially in older electrical systems. Nuisance tripping occurs when the GFCI trips even though there is no actual ground fault. This can be caused by a number of factors, including faulty wiring, loose connections, and electrical noise. If you're experiencing nuisance tripping of your GFCI, there are a few things you can try to resolve the problem. Firstly, check for faulty wiring. Make sure that all of the wiring in the circuit is properly installed and that there are no loose connections. Secondly, reduce electrical noise. Electrical noise can be caused by a number of factors, including fluorescent lights, computers, and appliances. Try to reduce the amount of electrical noise in the circuit by turning off these devices or by using a line filter. If you have tried these steps and the GFCI is still nuisance tripping, you may need to replace the GFCI. It is also important to note that GFCIs have a limited lifespan and may need to be replaced every few years. The coordination study, once completed, will provide guidance on the appropriate breaker settings. A coordination study is a detailed analysis of an electrical system that is performed to ensure that the overcurrent protection devices, such as circuit breakers and fuses, are properly coordinated. This means that the overcurrent protection devices are selected and set so that they will trip in a coordinated manner, isolating a fault to the smallest possible area of the electrical system. A coordination study is typically performed by a qualified electrical engineer. The engineer will collect data about the electrical system, including the size and type of conductors, the ratings of the overcurrent protection devices, and the loads served by the electrical system. The engineer will then use this data to create a computer model of the electrical system. The computer model is used to simulate various fault conditions and to determine the optimal settings for the overcurrent protection devices. The results of the coordination study are documented in a report. The report will typically include a description of the electrical system, a summary of the data collected, a description of the computer model, and a list of the recommended settings for the overcurrent protection devices. The coordination study report should be kept on file and used to guide the selection and setting of overcurrent protection devices. The coordination study should be reviewed and updated periodically, especially if there are any changes to the electrical system. If the 400 amps breaker is feeding 125 amps fuses, then the 400 amps breaker is acting as a main breaker. The purpose of a main breaker is to protect the entire electrical system from overcurrents. The main breaker should be sized to protect the smallest conductor in the electrical system. In this case, the smallest conductor is the 125 amps fuses. Therefore, the 400 amps breaker is properly sized to protect the 125 amps fuses. However, it is important to note that the 400 amps breaker may not be able to protect the 125 amps fuses from all types of overcurrents. For example, the 400 amps breaker may not be able to protect the 125 amps fuses from short circuits. Short circuits are very high current faults that can damage electrical equipment very quickly. To protect the 125 amps fuses from short circuits, it is important to use a fast-acting fuse. A fast-acting fuse is a fuse that will trip very quickly when a short circuit occurs. Fast-acting fuses are typically used in circuits that are critical to safety or where damage to electrical equipment is a major concern. If you are using a 400 amps breaker to protect 125 amps fuses, it is important to use fast-acting fuses. This will help to protect the 125 amps fuses from short circuits and other types of overcurrents. Remember to always consult with a qualified electrician for electrical work.